So now we are going to basically start with compression methods. And the first compression method we are going to do is Huffman coding. And definitely this is an algorithm which is very popular algorithm for coding redundancy technique. And this is a measure through which you can reduce the coding redundancies. And we have been all talking about the fixed length coding and variable length coding. So this will be my variable length code. And here what thing we are going to, or the idea or the intuition behind is that the minimum length code is assigned to the one with the highest probability. How this is going to happen, just see over here. Now suppose I have an image of 10 cross 10 and this is a 5-bit image, right? I have certain symbols like A2, A6, A1, A4, A3, and A5. The frequency of occurrence of these symbols is already given to you. So that is what they have reduced your task. They have not given a 10 cross 10 image and they have said, okay, calculate A2, A6. No, they have already given the frequency counts. They said that A2 is 40, A6 is 30, then 10, 10, 6, and 4. So what you need to do for Huffman coding is that firstly, you need to find the probabilities of these symbols. Now, probability of A2 will be 40 by 100, which is 0.4. Similarly, for A6 will be 30 by 100, which is 0.3. Then 0.1, 0.1, 0.06, and 0.04. You will make a table like this. Here you'll be writing all the symbols. Now these symbols, now you will be just confused about what symbols are these. These are some intensity values, right? So I've just given the name to intensity values, like A2 can be say 20 or A6 can be 25. So I have just given the names to these symbols, right? So we have A2, A6, A1, A4, A3, and A5. So these are the symbols given to me. I calculated the probabilities, but one thing you need to make sure is that we have written these symbols in decreasing order of probabilities, right? So highest is 0.4. So 0.4 is for A2, we wrote A2. Then second highest is 0.3, we wrote A6. So that's how you are supposed to arrange your probability. So we wrote 0.4, 0.3, 0.1, 0.1, 0.06, and 0.04. Now how you're supposed to start is start from the bottom and add the last two values, right? So we will go on doing this till we are just left with two values. And this is called source reduction, right? This is what we are going to do is source reduction. And one more thing, after adding these two, you have to maintain these things also in a sorted manner, right? So you have 0.06 and 0.04. Add them, they become 0.01. So 0.01, now list is still sorted. Now I'll add 0.01 and 0.01. This is 0.02. So it comes over here. Getting? So now I add 0.02 and 0.1. This becomes 0.3. I add 0.3 and 0.3. This becomes 0.6 and it comes over here, right? So after this all is done, now I need to provide symbols to it, right? Because I have to represent them in form of binary. Now we'll just see that how these symbols are allocated. Now I'll assign 0.6 with 0 and 0.4 with 1. So if here was anything say 0.7 and 0.3, so I'll assign 0.7 with 0 and 0.4 with 1. Now definitely I can interchange this as well. Like here I can write 1 and here I can write 0. But this is a convention which maximum books follow. So we'll have 0 on the top and 1 on the bottom. Now this 0.6 will backtrack and see from where it came. This 0.6 came from addition of 0.3 and 0.3. So what I'll do is I'll write this 0 over here. I'll copy this 0. And then again I'll write what? I'll append 0 to the first value and 1 to the other value, right? So I just took 0, I wrote it over here, and then I appended 0 over here and 1 over here. Similar fashion I'll be following throughout. Like this 0.3, this 0.3 came from addition of 0.2 and 0.1. So 0.3 is having value of 0, 1. I'll write 0, 1 over here and 0, 1 over here. Now append 0 here and 1 here. So this will have 0, 1, 0 and 0, 1, 1. Now this came from what? Addition of 0.1 and 0.1. So this is 0, 1, 0. So I'll write 0, 1, 0, 0, 1, 0. Append 0 over here, append 1 over here. Now this 0.1 came from these two. So this is 0, 1, 0, 1. I wrote 0, 1, 0, 1 over here, 0, 1, 0, 1 over here. Append 0 here, append 1 here. And that's how till here you are able to calculate all the probabilities. Now we have to see the codes for this. We got the code for A3, which is 01010. For A5, we again got the code 01011. So now let's see that what is the code for point 4. For this, you have to trace that where point 4 is. Okay, so in first iteration, point 4 is here, it is here, it is here. Now, during the sorting, it went here. So point 4 is having code 1, so I wrote over here 1. Now let's see the code for point 3. Just trace where my point 3 is. Point 3 is here, point 3 is here, point 3 is here. So this is 0, 0. So I wrote the code 0, 0. Now let's see the code for point 1. I traced point 1 is here, but due to sorting, it went here. So here this is 0, 1, 1. So I wrote 0, 1, 1. Now trace this point 1. Where is this point 1? It is here. It is here. And what is the code for this point 1 is 0100. I wrote 0100. So this is how you calculated the codes. And this is nothing but the code for A2. A6 having the code 00, A1 has a code 011, A4 has a code 0100, A3 has a code 01010, and A5 has a code 01011. Now, this is how we encoded it, right? So supposedly there was some message. I was the sender, right? And I encoded the string. And whatever message I wanted to send, I encoded it, and the message was 010100, 4 times 100. Now the receiver has to decode it as well. Now, how we can decode it, right? So this is a beauty of Huffman coding, that you can decode it very easily, right? How am I going to do this? Read the symbol from left, read one symbol at a time, just search that if that one symbol exists or not, and if it exists, write the code for it, and if it doesn't exist, then take two symbols, see if those two symbols exist or not. Like, you will get to know, right, what I'm talking about. Just take over here. We'll first see, look for 0. Does 0 exist in my code? No. I'll see for 0, 1. 0, 1 exists in my code? No. 0, 1, 0. No. 0, 1, 0, 1. 0, 1, 0, 1. No, there isn't. 0, 1, 0, 1, 0. 0, 1, 0, 1, 0. Yeah, it is A3. So I wrote A3, right? Now I'll again look for 0. 0 in the code? No. 0, 1 in, okay, next is 0, 1 in the code. Okay, well, 0, 1, no. 0, 1, 1 in the code, yeah, that is A1. So I wrote A1 over here. So definitely I had 0, 1, 1 here. Do I have a 1? Yeah, I have A2. Do I have a 1? Yeah, I have A2. Then do I have a 0? No. Do I have 0, 0? Yes, that is A6. So that's how you go for decoding, right? Now, after you've done all this algorithm, there are certain calculations we want to see so that we can understand the beauty of this algorithm, and we can appreciate that, wow, what a wonderful job it is done, right? So first is the average length of the code. The L average, you know how you're going to calculate. We did it already. Just pause the video and just see how to do it. So we have 0.4 into how many symbols? 1. 0.3 into 2, because there are two symbols required, plus 0.1 into 3 plus zero point 0.1 into 4 plus 0.06 into 5 plus 0.04 into 5. So this gives me 2.2 bits per symbol. Else we were having it as 5-bit image, right? So we would have required 5 bits per symbol, because that is given to us, right? That it's a 5-bit image. So you just saw that we just saved quite a bit, right? So what are the total number of bits which are to be transmitted? That will be definitely m into n into L average. So 10 into 10 into 2.2 gives me 220 bits. Next is entropy. How you can calculate entropy is nothing but minus probability into log of probability. So this is minus 0.4 into log base 2.4 minus 0.3 into log base 2.3, then minus 0.1, so on you can do, and this comes out to be 2.1396. Now how much you saved, right? How you can do it? This is, earlier you were supposed to transmit this much, 10 into 10 into 5, because it's a 5-bit image. So number of rows into number of columns into bits per pixel. So minus Now it is what? 10 into 10 into 2.2 divided by what it was initially. So this is kind of the same as the formula we did for relative redundancy, right? Which is L average minus H by L average. So this is also the same formula. This is 0.56, which is 56%. So you saved 56%. That's the beauty, like 56%. That is so much, right? So supposedly, like just a very vague thing I'm saying, that if my supposedly initial file was of 2 GB, right? So now I'm just having what, 1 GB nearly. If I take it approximately like that, so you just see how much difference is that, right? So this is one more example. You can try to do it and just pause it and do it. This is a homework. I leave it as a homework for you. This is the 8 level image. It has gray level distributions. So you are given, now instead of A1, A2, A3, they are just given 0, 1, 2, 3, 4, 5, 6, 7. Probability is given. This is how you do it using normal fixed length code. But now we know Huffman coding and we'll be trying to see if there is any redundancy or not. Now, the question which definitely comes or arises is that why can't I use random codes? Random codes means that, okay, I just saw this is having probability 1. What if I assign 0 to this, 1 to this, then I assign 0, 0, 0, 1, 1, 0, 1, 1. What about this? See, in that case, the coding will be very difficult because if I say, okay, 0 to this, 1 to this, 0, 0, then if there is written 0, then I could write it as A6, A6 two times, or I could write it as A1 one time. So it would be so much hodgepodge or a mess which will be there, right? So what is the beauty of this Huffman is that it enables the decoding very easily and there's no ambiguity in the decoding, right? And one more thing which is not mentioned over here, but this is something practical. You won't find it in your textbooks or somewhere else. In decoding, we say that, okay, we saved this much amount of bits. We generally say, but practically what happens is that you also need to send a key table in which you have to say that, okay, my A2 is 1, my A6 is 0, 0, because else how would my receiver, decode these things? So you have to send a table as well, right? So there comes the size of table and then you are able to calculate the exact how much you saved, right? So for that, that is something which happens just practically. So don't worry about that. And that's all, and have a great day.